Section 6.5 is properties of logarithms, and so we're just going to continue our discussion we started in section 6.4 with the logarithmic function and look at some specific properties of logarithms and how those might be useful for us. And so we're just going to dive right in here just with a couple of properties to start here. It says there's several useful properties of logarithms which can be derived from the definition of a logarithm and the laws of exponents. And so the first one, it says show that log base a of 1 equals 0. Okay. Well, if we want to look at log base a of 1, we can rewrite this. We say it's equal to x. We could rewrite that as a to the x equals 1, right? From there, using our properties of exponents and trying to solve this equation for x, 1 is the same as a to the 0 power. And so from that, you get that x equals 0. So in other words, log base a of 1 equals 0, which is what we were supposed to show. And so that pretty well shows that property, kind of proves it. And what that essentially means is that it doesn't matter what the base of your logarithm is, if you have a 1 as your argument there, then the result is 0. So you could say natural log of 1 is 0. You could say log base 10 of 1 is 0. Log base 17 of 1 is 0. Doesn't matter what the base is. The result is always 0 if you've got this 1 right here. That's kind of what that property says. The second property here that says show log base a of a equals 1. So let's kind of start out the same way. What's log base a of a? We don't know, so let's call that x. So a to the x equals a, which is the same as a to the first power, right? So x has to be 1, or in other words, log base a of a equals 1. And so that's our property. And essentially what this says is if those two match, then the result of that logarithm is 1. So we could say log 10, common logarithm, base 10 of 10 is 1. Natural log of e, so base e, is 1. Log base 20 of 20 is 1. Okay, that's what that property says. Pretty simple, straightforward stuff. Okay, the next two properties, these go back to the fact that logarithms and exponential functions are inverses of each other. So that's essentially what these two right here are saying. It says if we take a base a and raise it to the log base a of m power, the a being raised to a log base a power essentially cancels out and you get an m. So m equals m. Same thing here, log base a of a to the r power. Taking a base a logarithm and dropping an a to the r inside of it, the logarithm and the base a to the power cancel out. And again, this just goes back to the fact that these are inverses of each other. Now we can show that these two properties are true if we take f of x to be log base a of x and g of x to be g of x can be a to the x. So using what we know about inverse functions, if we do the composition, back up here, we do the composition f of g of x, then that's f of a to the x, which is log base a of a to the x, which we know, since those are inverse functions, the result has to be x, right? And then, if we switch it around, do g of f of x, do the same thing. That's g of log base a of x, which is a raised to the log base a of x power, which again, inverse functions, has to equal x. Now if you compare this with this, instead of r's, use x's. You can see that's basically what that says there. Same thing here if we go up take this, replace the x's with m's, we get this guy, right? So those are the same. Those are equivalent, and that shows that those two properties are true. The way we can use those is to help simplify some logarithms. And so if you have a base of 2, and then notice this exponent is a base 2 logarithm, essentially those cancel out, is what this is saying, and so the result's just going to be pi. Here, this 0.2 base in the logarithm, and here's 0.2 as a base for an exponent. Those cancel out. You get negative square root 2. Here, natural log of e to the kt. Remember, natural log is the same thing as a log base e, right? So those cancel out, and you get kt. And so that's how that's used, just to simplify whenever the base of the exponent matches the base of the logarithm, and it's a composition of the two. Okay, these next three properties look like a lot to take in, but they're not too bad. They're related to some properties of exponents, but what this says is if you have log base a of m times n, you can break that off into two separate logarithms with a sum in the middle. So multiplication inside logarithm becomes a sum. Here, if we divide, it's the same thing, but we subtract the two logarithms. And then here, what this property, this last one on the page, says is if we have log base a of m raised to the r power, so if we have a power on that argument inside the logarithm, we can actually bring that down, and it becomes r log base a of m. And the details on why these properties are true, they're in the textbook if you want to look on page 452. You don't really need to know the derivations for these, and so feel free to look at those if you'd like, if you're wondering why that's true. It really relates to some properties of exponents we have, just to kind of get you thinking in the right direction. This first property here is sort of equivalent to when we have like a to the m times a to the n equals a to the m plus n. Those is kind of the equivalent property for those properties of exponents. And so that's the idea there, but just know that's kind of how these properties work. A product inside a logarithm can become a sum of two logarithms. If we divide, it becomes a difference of two logarithms, and then a power right here we can bring down front as a product, r times log a of m. Alright, so with that in mind, we can actually look at taking all these properties and